Welcome to the Explainer. Today, we're stepping right into the high-stakes, super delicate balancing act of nuclear physics and reactor design. Sustaining a nuclear chain reaction, well, it's basically a microscopic puzzle, but it has massive, and I mean literally massive, global energy implications. And today, we're going to break down the exact mathematical budget engineers use to actually solve it.
Okay, let's dive into this with a pretty fundamental question. Can we, in principle, build and operate a thermal reactor if enough quantity of the right type of fuel is available? Now, it sounds simple, right? Just gather enough fuel and let the physics take over. But here's the catch. Figuring out exactly what that right type of fuel is, well, that's a seriously complex engineering challenge governed by some very strict mathematical rules. Let's see if we can solve it together.
To figure that out, here's a quick roadmap for this explainer. First, we'll look at the chain reaction rule. Second, the thermal reactor solution. Third, the fast reactor alternative. And finally, number 4, mixing the perfect nuclear fuel. Don't worry, we're going to demystify all this complex physics step by step.
All right, let's jump straight into Section 1, the chain reaction rule. This is the fundamental problem every engineer faces when trying to sustain a nuclear reaction.
By pure common sense, if you want a chain reaction, your fuel absolutely has to have a higher probability of fissioning than just absorbing or capturing a neutron. And that gives us our ultimate golden rule, the strict mathematical budget required for any reactor to work, the fission-to-capture ratio, or FC. Whenever a neutron strikes a fuel, the ratio of its fission probability to its capture probability has to be strictly greater than unity, meaning greater than 1. If it drops below 1, the whole reaction just fizzles out.
And this brilliantly illustrates the whole challenge. Looking at the cross-section data for natural uranium, you can see the problem right away. The numerator, that's the fission part of our ratio, well, that's entirely dominated by a tiny fraction, just 0.7% of uranium-235. But the denominator, that is completely dominated by the massive 99.3% bulk of uranium-238, which basically just sits there constantly capturing neutrons without actually fissioning.
So, how do we fix that? That brings us to Section 2, the thermal reactor solution. This is our first major engineered fix for that golden rule, and it's all about what happens at really low energies.
Now, what's really interesting about this slide is that enormous spike all the way over on the far left. See that? That is the low energy region. Over there, the line literally rockets up well above the 10 to the 0 mark, which is our unity line of 1. By slowing the neutrons way down into what we call the thermal range, the FC ratio of natural uranium spikes well above 1. Boom, chain reaction achieved.
Because of that incredible low energy spike, thermal reactors have completely dominated the worldwide landscape. Now, to make this work, they absolutely require a moderator, think water or graphite, just to put the brakes on those neutrons and slow them down. And by significantly reducing that neutron speed, you can get away with using fuel that has a very low fissile fraction. It's a highly prudent option, because it means you can use natural uranium straight out of the ground, completely avoiding the need for heavy, expensive modifications.
But what if we don't slow them down? Let's shift gears to Section 3, the fast reactor alternative. This introduces a completely different set of challenges.
Now, quick clarification here. When we say fast reactor, we are talking strictly about the dizzying kinetic energy of the neutrons themselves, not, how quickly the construction crew built the actual power plant. In this fast energy region, these little guys are zipping around with energies between 100 and 500 kiloelectron volts. It's wildly fast.
Let's do a quick head-to-head comparison here, so you can really grasp the core engineering differences. A thermal reactor uses a low fissile fraction, but it totally relies on a moderator to work. A fast reactor, it completely flips the script. It operates without a moderator at all, letting those neutrons stay incredibly fast. But to pull that off, it absolutely requires fuel with a very high fissile enrichment.
So the crucial point is this. In that dizzying 100 to 500 keV region, the natural FC ratio plummets all the way down to between 0.06 and 0.09. I mean, that is nowhere near unity. To force that ratio back above 1, you literally have to enrich the fuel to nearly 20%. And let me tell you, enrichment is a massively expensive reality, plus it depletes our natural U-235 way faster. But wait, here is the massive upside. When you use these fast reactors with man-made fissile material, they can actually breed more fissile material than they consume. It's almost like a car magically making its own gas while you drive.
Which perfectly tees up our final act, Section 4,
mixing the perfect nuclear fuel. Finding the right fuel is an incredibly delicate Goldilocks balancing act. Just take a look at this staggeringly low number straight from the data, 6.0 times 10 to the negative 6. That is the FC ratio of 100% pure uranium-238 when hit with slow neutrons. It is essentially zero. This visually proves exactly why you cannot just build a reactor using pure fertile material. It's a total dud. It simply will not ignite a chain reaction. No way.
Okay, so you might be thinking, why not go to the complete opposite extreme? Why not just use 100% pure U-235? Well, a reactor stuffed with pure fissile material drives the FC ratio way, way too high. Yes, you desperately want a ratio that exceeds 1, but an overly high value, that is a huge problem, because it makes it virtually impossible to safely control the chain reaction. It's basically too much of a good thing.
And this table right here ties the whole puzzle together. Engineers have to carefully blend isotopes to find a mixture that is just right. Pure U-238, dead in the water at 6.0 E6. Pure U-235, dangerously reactive at 5.9. But look at the middle ground, natural uranium. In a slow thermal reactor, that specific natural blend hits a perfectly manageable ratio of 1.22. It comfortably clears the unity hurdle, but it remains completely controllable.
So all this microscopic physics leaves us with a pretty massive real-world question. We know that relying on natural uranium is actively depleting our only natural fissile resource. We also know that fast reactors, which use much more complex mixtures, can actually breed brand new fuel. So with natural uranium depleting, will the highly enriched, expensive, fast fuel mixtures of tomorrow actually be worth the massive upfront investment to secure our global energy future? It really is the defining question for the next generation of nuclear engineers. Thanks so much for joining me on this explainer, and hey, keep questioning the science around you.